Now we're going to jump in and talk about how stuff moves across the membrane and what types of molecules can go across the membrane and just how that works. What's driving that process of moving material across the membrane, right? Because everything that cell needs to stay alive, all of its food it brings in, all the gases it needs, all the water it consumes, everything it needs to stay alive has to come through that membrane. And everything it needs to get rid of, all the waste it needs to excrete, also goes through that membrane. So understanding how these membranes function gives us a really great insight into how cells function and how a lot of our medicines often, or treatments, influence the permeability or the reactivity of cell membranes. Okay, so again, plasma membrane, it is the barrier between the cell and everything outside the cell, okay? So it controls what comes in and what goes out of the cell. So it's transporting materials across the cell, either into the cell or out of the cell. But how does it do this, right? Well, part of it is all the proteins that we talked about, but what exactly is moving into and out of the cell? So we say that the plasma membrane is selectively permeable, meaning that it will let some things through, but not everything. Okay, so here's where we talk about what can come through and how does it move through. So, the plasma membrane, remember that phospholipid bilayer, it's hydrophobic in the middle and those hydrophilic heads on the outside. Because of the nature of that hydrophobic middle to our phospholipid bilayer, usually only small non-charged molecules, only small hydrophobic molecules can move through the plasma membrane directly, not necessarily requiring a protein to transport them. So some molecules, like oxygen, carbon dioxide, nitrogen gas, benzene, they're very small, they're non-charged, they can fit through that plasma membrane directly. Okay? Anything that is charged or relatively large cannot fit through that membrane very well. Okay? Ions, definitely not. So if it has a positive or a negative charge to it, hydrogen, sodium, bicarbonate, chlorine, magnesium, calcium, right? Those ions, nope, they're going to be repelled by those hydrophobic tails of the phospholipid molecule, right? Water can kind of squeeze through, so small charged polar molecules can kind of squeeze through, but they're really slow at moving through, okay? And large polar molecules, definitely much, much, much slower. The larger you are, that's just the harder it is to fit between those tails, okay? So I kind of made up this stupid little rhyme to remember it. Large and charged will not come through. Okay, I don't know if that helps. Large and charged, nope, will not pass through the membrane. But if it's small and non-polar, then it can pass through directly through that membrane. Okay, so if those molecules will not fit directly through the membrane, how do they get across the membrane? Proteins, right? Proteins basically do everything in a cell, so it makes sense that proteins would be responsible for moving molecules across the membrane. So we have generally two types of proteins that help move molecules across the membrane. We call them transport proteins. The first type just being channel proteins. So channel proteins let basically molecules of a certain size and shape and maybe polarity squeeze through that membrane. It's like a little tunnel through the membrane that these molecules can go through. Okay. So for example, we have in our cell membrane aquaporins, are specialized proteins that just let water through. Okay, so they have the chemical and physical properties that allow water molecules through, but they don't let really anything else through, okay, besides water. So different molecules will have different channel proteins in them, and they're again just a tube. They're basically just a little straw through that membrane in which molecules can move through. And then we have carrier proteins. So carrier proteins are slightly different, okay, than channel proteins because their process of moving molecules across the membrane requires a shape change. So usually when proteins bind something else, they will change shape. Binding molecules together, especially proteins binding something, causes them to change shape, right? So what happens here is that whatever solute the cell is trying to move across the membrane will bind to this carrier protein That process of the solute binding to that protein causes it to change shape, and then that shape change basically causes that carrier protein to deliver that solute to the other side of the membrane. So those are the basic classes of proteins that are used to move molecules across the membrane. We're going to focus on first passive transport. Okay, so passive transport is kind of what we've been looking at here, where molecules are moving, what we say, with their concentration gradient. So in passive transport, the cell does not expend energy to move molecules across the membrane. No energy is expended, okay, to move material across the membrane in passive transport. That's why it's passive. Okay, so let's break this down and talk about what exactly is happening in passive transport. What are the forces that drive passive transport? So this first idea that we need to get to kind of wrap our heads around is called Brownian movement or Brownian motion. And that's the idea that whenever molecules or atoms or ions, whenever stuff's in a solution, whether gaseous or liquid, it's constantly in motion. That's what I have this GIF here for. All of those balls bouncing around, those are all representing atoms or molecules in solution, dissolved in, let's say, water maybe. Maybe the blue molecules are water molecules and the red are solute. When they're in a solution, they are constantly in motion. Molecules are constantly moving and bumping into each other and moving and bumping into each other and bumping off, right, colliding with each other. That motion is really driven by thermal energy. How warm that solution is, the faster the molecules will move. Side note, Brownian motion is also influenced by the mass of the molecules, the density of the medium, in addition to temperature. So the more mass a molecule has, the slower it moves. The more dense the medium, the slower Brownian motion happens. And the colder the temperature, the slower those molecules are moving in that Brownian motion movement. Okay, back to your regular scheduled program. So everything is constantly in motion, both outside the cell and inside the cell. Okay, so that's our first idea that we need to understand in order to process how passive transport works. Brownian motion, this random bouncing into each other and bouncing off, this random movement, drives diffusion. So diffusion is the idea that due to that random motion of bouncing into each other, molecules will tend to move away from each other. They'll tend to spread out, basically. That's basically what diffusion is, right? So I like to think of this kind of like if you're like baking cookies, right? The molecules, those cookie molecules that make it smell so good, probably those fats and those sugars all combining together, right? And those carbohydrates, they will be most concentrated at their source in the oven, right? But over time, especially when they're close to being done, right? When they've been in there for about like 15 to 20 minutes, right? You can start to smell them throughout the rest of the house. So that's because those molecules that give cookies their smell are diffusing. Okay, so that Brownian motion, that random bumping into each other, that causes molecules to move, and it ends up with molecules bumping into each other and eventually taking up all the space that they can, moving as far away from each other as they can. They kind of reach this equilibrium point where they maximize the distance between other molecules. Okay, so they fill up the space that's around them in order to maximize the distance between other molecules, and that is driven by that random movement, that Brownian motion. So molecules will tend to move. So let's say we sprayed like some perfume molecules right here. Over time, molecules will tend to move, these perfume molecules will tend to move from areas of high concentration, right where we sprayed them, to areas of lower concentration, right? So over time, they will spread themselves out, and that's diffusion. Molecules moving from high concentration area where there's a lot of them to a lower concentration area. Now, all we're going to do is throw a membrane in the middle of this, and if those molecules can fit across the membrane, they will diffuse across the membrane. And ta-da! We have passive transport. So, particles will follow that process of moving from an area of high concentration to low concentration across a membrane, if that membrane has space for them to diffuse across, or if they're a molecule that will move across that membrane. Right, so here we have a fake membrane with tiny little holes, and some of these molecules, we have a dye here, let's say maybe it's a blue dye or something, and those molecules will tend to diffuse over time across that membrane from a high concentration area to a lower concentration area, because they're constantly bouncing into each other, right? So that Brownian motion causes these molecules to move around, they're bouncing into each other, some of them will bounce across that membrane, but over time we'll see they'll reach an equilibrium where there's roughly the same concentration of those molecules on either side. Okay, so they've kind of distributed themselves out so that way they're in equal concentration on either side through the process of diffusion. Okay, so molecules will tend to move from high to low concentration until they reach an equilibrium state. And they're still moving in equilibrium, but there's no net difference in the concentration of those molecules on either side of that membrane in equilibrium. Okay, so how does this apply to cell membranes? Well, the number one thing that I want you to remember about diffusion, which is the main process behind passive transport, is that molecules will always move down their concentration gradient. They will always move from wherever there's a higher concentration of that molecule to an area of lower concentration. Okay? This is our number one rule. We always, in passive transport, molecules will tend to move down their concentration gradient from high to low concentration. Got that? This is super important because this explains how osmosis works too, which is where we're going next. Alright, so we just take that idea of diffusion, put a membrane in the middle, molecules moving with their concentration gradient across a membrane is passive transport. That's basically it, right? So let's say we have, I don't know, maybe these are oxygen molecules, right? Oxygen is small and not charged, so we can fit through that membrane. So over time, if on one side of the membrane we have a high concentration of oxygen, the other side there's no oxygen over here, so there's zero concentration of oxygen. These molecules will tend to diffuse across that membrane until there's an equal concentration on either side. This process just happens due to Brownian motion. It does not require the cell to expend any energy, therefore this is a type of passive transport. No energy was used by the cell. Molecules moving from high concentration to low concentration until they reach equilibrium without using any energy is passive transport. A variation on this idea is facilitated transport. Still type of passive transport in the sense that the cell is not expending energy, but now we just need some proteins to help out, right? Those channel proteins or those carrier proteins that we just talked about, now we put those in the mix and they just help molecules move with their concentration gradient. Again, no energy is being expended here, okay? But molecules that cannot fit directly through the membrane can now move with their concentration gradient if they're moving through one of these carrier proteins. So we have a higher concentration on one side of the membrane than the other. Those molecules will tend to diffuse with their concentration gradient, high to low concentration, but instead of fitting directly through the membrane, they're moving through these proteins. And that's all facilitated transport is. It's a type of passive transport that utilizes proteins to help molecules move down their concentration gradient. Again, no energy is used here. This just happens as a result of diffusion, which is the result of Brownian motion.